Hello. So, in the last class we learnt about elliptic PDEs and few techniques. So, with this we covered parabolic and elliptic PDEs. So, now let us move on to hyperbolic. So, before we go for finite difference approximations, it is worth to spend a few minutes on the corresponding analytical treatment in brief. Okay. So, the typical example of a hyperbolic PDE which is generally taught in first course is a wave equation. Okay. So, let us review wave equation and then proceed to the corresponding finite difference approximations. Okay. So, we review wave equation. Okay. So, which is defined as so this is infinite string problem and we have various versions fixed at one end. For example, if it is fixed at one end, then one end will be infinity, other end will be the corresponding point where it is fixed at both ends. So, then it will be an interval a to b. Okay. So, now we have to define the complete problem by specifying the corresponding initial and boundary conditions. Okay. So, we have these are initial conditions. So, what are these specifications? So, here the dependent variable u, this denote displacement. So, dou u by dou t, so this denote velocity. Okay. So, the initial conditions are given initial displacement as f of x, initial velocity g of x. So, we are looking for the solution and in the present case, since it is infinity, I would like to put it so this displacement, this is typical, though for fixed boundaries one may have a function of t, but in general far field if you see displacements are generally vanishing displacements. Okay. Because if you, for example, if you fix and then so pull, so you will have vibrations, then maybe they will die down slowly. Okay. So, you have some vibrations back and forth and then at far field they die down. Okay. So, this is the complete definition of the problem and analytical point of view, there is a popular solution known as Dialombet's solution. So, this is given by okay, plus 1 by 2 c So, with these given initial velocity as f of x, sorry, initial displacement is f of x and initial velocity is g of x. So, then the solution is given by this. If g of x is 0, that is initial velocity is 0, then e of x t is so this would be the solution. So, these represents two waves. So, this represents two waves each equal to f of x by 2 with speed c, one to the left and one to the right. Okay. So, for example, let us consider some initial profile, say f of x is given by okay. So, if such a profile is given, then what would happen? So, this is x axis and t axis. So, we have -1 1. So, this is f of x. So, these are f of x by 2, say this. Okay. So, this is at t equals 0, which is this profile. So, then what would happen correspondingly? So, this is at t equal to 1 by 2 c, and further so this is at t equals to 1 by c. Okay. So, then again after some time this is at t equals to. So, that means with this initial profile, as time progresses, one wave passes to the left, another wave passes to the right. Okay. So, this is popular Dialombet solution, which explains the physical significance of the solution. Okay. So, similarly, there could be other case corresponding to f of x equals to 0. So, this is a special case. Okay. Suppose if f of x equals to 0, then we have u of x t is okay. So, this will be where g of x is okay. So, again for a given initial g of x, we can see how it progresses. Okay. So, this is at least it is useful to understand the analytical solution, which is a Dialombet solution, and the corresponding physical significance. So, now when you see the waves are passing one to the left and one to the right. Okay. So, initially when we have given initial, okay. So, this point has been displaced to the maximum extent, right. So, now it is useful to understand something called range of influence, sometimes domain of influence. So, which means domain of influence of the data at x equal to x naught initial point on the solution. So, this domain of influence of the data at x equal to x naught on the solution. So, this consists of all points closer than C t to x naught. So, what do you mean by that? Okay. Suppose if we take initial point, then domain of influence of the data at x equal to x naught on the solution. That means, how far this would influence the solution. This is with slope, these are the corresponding slopes. So, this is the domain of influence of x naught on the solution. Okay. Similarly, we have domain of dependence. So, domain of dependence of solution on the initial data. So, this consists of all points within a distance C t from the solution point. So, this is range domain of influence of x naught on the solution, and here it is the opposite. So, domain of dependence of solution on the initial data. Okay. So, this would be so these are x minus C t, x plus C t 0 0, and this is a point x t solution point. So, this is domain of dependence of solution on the initial data, consists of all points within a distance C t. Okay. So, solution data. So, this solution depends on the initial data within this range. Okay. So, these are few important remarks about the wave equation. Okay. So, now let us proceed to the finite difference schemes. So, to start with we go for usual approximation and then see what will happen in under what conditions we go for explicit and under what conditions we may arrive at implicit scheme. Okay. So, let us start with a simple normal usual discretization. Okay. So, finite differences wave equation. Okay. So, consider with initial conditions and the boundary conditions. So, when I say suitable, so this depends on the problem. So, this depends on the domain. So, for example, if it is fixed at both ends, so then what we expect, u of a t is some u a, u of b t is some u b. Of course, they can be functions of t. Okay. So, now we discretize this. So, go for central. So, then we arrive at okay. So, now this we can simplify. So, if you simplify, where lambda equals to k c by h. So, what we have done, we just adjusted. So, this is we need at a higher time level. So, we have written this to the left hand side and the remaining terms got adjusted. So, when we take this h square, so h by c k, h by c k is 1 over lambda. So, accordingly that got adjusted. Okay, c square by k square comes here. So, c k by h whole square, which is lambda square, and then we got adjusted. Okay. So, the remark here is the coefficients are as follows. The grid is as follows. So, this is I j, I j, I plus 1 j, I minus 1 j, then I j minus 1, and we have. So, we are looking for the value here, and it is asking. Interestingly, if you see to the right hand side, it is asking data at 2 time levels. Okay. So, if the data at levels j and j minus 1 are available, one can compute the values at level j plus 1. So, hence this is explicit in this sense, however, 3 levels are involved. Okay. So, this is explicit in this sense, however, 3 levels are involved. Okay. So, let us have a quick look at the corresponding error involved. So, let us expand this equation. So, consider so this is approximately equals to 0. So, if we expand, so this term I am expanding, minus 2, of course, all of these evaluated at x I y t j. Okay. So, this term is done, then this one minus lambda square u I j minus dot dot, then we have minus lambda square, I mean this is u and plus h So, we have done earlier. So, by now you should be conversant with this technique plus u I j minus 1 minus k Okay. So, now let us count. So, we have this term get cancels, okay, and this term get cancels. Okay. Then look at, there is one u I and we have another u I. So, we get 2 u I, then we have a minus lambda square u I and another minus lambda square u I. So, these terms cancel. Okay. Then which of the terms get cancelled. So, minus lambda square remains. So, this these terms get cancelled. Okay. So, if you count it, ultimately we get this minus lambda square etc. So, this can be written as k square plus k by 12 Okay. So, we can simplify and ultimately k power minus 2 truncation error goes to plus, so there is a k square, this is x 4 minus h square. So, which is of order, because this goes to 0. So, the order of the error is this much. Okay. So, however, let us observe closely the equation, which equation? This one. So, as I mentioned the remark, we need two time values at two past time levels, j minus 1 and j. So, let us see how we can proceed with this. So, the remark is u I j plus 1 is so, given this, in order to start the computation, one need data at two past time levels. So, this is the remark. However, consider dou u by dou t at x equals 0 is. So, this is one of our initial condition, this is initial velocity is prescribed. So, we make use of this G I. Of course, this is of order, because this is second order. So, now this is at x 0 we have j is 0. So, this implies u I 1 minus 1 by 2 k is g I. So, I can write this is some A. So, this implies, so these are the values, past values. So, u I minus 1 equals to u I 1 minus 2 k g I. So, this is B. Okay. So, when we, let us say we want to compute at j equals to 0. So, this is at 1, then 0, 0, 0, then we need at minus 1. So, these fictitious values can be eliminated from here. Okay. So, now let us consider A at j equals to 0, because that is where we get a fictitious value. So, we have u I 1 u I 0 So, then we can substitute this value. So, this is so we can 2 times and then we can divide. So, ultimately we get u I 1 equals to so this 2 gone plus k g I. So, I did not do anything. So, one step I skipped. So, this will be 2 times. So, everywhere you divide by this. So, you get this. So, therefore, so this is at first time step, because you can see at first time step using at 0 time step we can get explicit values, then so this is at so this is explicit scheme for the wave equation. So, at first time step we use this, then for the higher time levels you can see we can compute with this. Okay. So, this is an explicit 3 level. So, this is explicit 3 level scheme. So, let us solve a problem. Okay. So, as you can see this is very initially it looks a little difficult task, but when we have discretized the corresponding initial velocity, the fictitious values are removed and hence we got the corresponding fictitious values removed, and then we got one equation at first time level, and then for the remaining we have another equation. Okay. So, let us consider an example. So, an example, so I have changed the notation and then C is 1. So, you can understand. Then so this is our g of x. Okay. So, these are initial conditions and these are boundary conditions. So, now we need to know h is 1/4, lambda is half. So, accordingly we solve for the time levels. Okay. So, now consider the boundary conditions. E of 0 2 is 0. So, this implies u 0 j is 0, e of 1 t is 0, 1 corresponds to 4, 4 j is 0, and initial condition u of x 0 is x. So, this implies u I 0 is x I, and the corresponding discretization I would like to show the next sheet. So, dou u by dou t x 0 is g of x, which is equals to x in our case, and from the previous discretization we have obtained, you can see. So, we make use of it. So, u I 1 equals lambda square by 2 plus k x I, and in this case k becomes, in this case k becomes 1 over 8, because we have okay. So, we have right. So, now let us compute the values at each nodal point. So, we have this 0, 1/4, half, 3/4, 1. Okay. So, u 1 1 equals lambda square, lambda square is 1 over 4. Okay. So, this becomes 1 over 8 u 0 0 plus 1 over lambda square, 1 minus lambda square. So, this will be 3 by 4 u 1 0 x 1 by 8. So, x 1 is this. So, 1 over 8 into 1/4. Okay. So, this can be obtained u 0 0. Okay. So, this is 0 plus 3/4 u 10, u 10 is x 1. So, we have u I 0 is x I, the remaining are 0. So, this is 1/4, this is half. So, this is calculated and so please check it. So, then u 21. So, u 21 means, so the grid is like this, it is asking. So, this is j equals to 0, j equals to 1, j equals to 2. So, in this case the method asks j equal to 0 and j equals to 1. Okay. So, in order to compute j equals to 1, we made use of this equation, that is what we are doing. At each grid point using j 0, we are computing at j 1. So, that we use the other formula and compute. Okay. So, u 21 is 1/8 u 10 x 2. Okay. So, this will be 1/8 u 10 is x 1, that is 1/4 is half 3/4. So, this is obtained as okay. Then similarly, we obtain u 31, we obtain 1/8 u 20, u 30, u 40, x 3. So, this is 40, this is u 40 is x 4. So, that is 1, just a second. So, this is at 3, I equal to 3. Okay. So, this is 40. So, this is 1 plus, so this may be computed. Okay. So, now we have obtained all the values required to compute at other time levels. These are the first time level. Okay. So, now we proceed at higher levels. So, at higher levels, so let us consider j equals to 1, then so this is at second level at all grid points. So, now we can use this and compute at each. So, for example, u12, so this must be I general case, I am sorry, this is I plus 1 I. So, in this case, so these values are substituted. So, just now we have computed u11. So, these values will be used. Okay. So, you may verify. So, this is the value at first grid point, then I equals to 2. So, this will be 3 1 we have calculated earlier. So, this we have got. So, similarly, so we can compute. Okay. So, this is very straightforward. Once you get the values at first time level, so then higher time levels can be obtained by the finite difference scheme, which is more general. So, it is a combination of two expressions. First one is at first time level, then the rest is for any general j. Okay. So, with this one can march past and compute at higher levels. So, this is very explicit method. So, now let us review, let us see under what situations we get implicit method. Okay. So, consider u I j plus 1 So, this is a 3 level explicit method which we have derived. Okay. So, now this I would like to just put it in a slightly different form. So, the same one. Now, what we are going to do is replace uij on RHS by so we want to bring in more time levels. So, then only this becomes implicit. So, what we are trying to attempt? We are trying to attempt implicit method. So, all that we are doing is introduce more time levels. Okay. So, let us see what happens. So, here so when I say RHS uij, that means data at jth level would be replaced. Okay. So, now this is at jth level. So, we manipulate the index for I j, this is the rule. So, correspondingly for I minus 1 j, so this remain then we have j plus 1, j minus 1 by 2, then we have 2 times u I j by 2, then we have okay. So, this is lambda square, then we have plus 2 by 2 minus okay. So, this is not replaced because this is containing at j minus 1 time level. Okay. So, what did we do? We have replaced all the data points on the right hand side which are at jth level by average of j plus 1 and j minus 1. So, you can see we are expanding the scope. So, we expect more accuracy. Okay. So, this is general idea. Okay. So, accordingly we have manipulated the corresponding index notation. So, for u I j this one. So, for u I minus 1 j. So, I minus 1 j plus 1, I minus 1 j minus 1 accordingly. Okay. So, now we can simplify. So, we can simplify and see. So, you have various terms. For example, this is u I minus 1 j plus 1 and this is I plus 1 j plus 1, right. So, some terms are expected to be cancelled. Let us see u I j plus 1, u I j plus 1. So, we do not have any. Okay. So, this reduces to u I minus 1 j plus 1 So, if we adjust these, if we adjust this, so this is lambda square here. So, we have replaced, then so we have to rearrange these terms. So, then when we rearrange these terms we get, so which is implicit scheme. Okay. So, we can see how this would come up. So, we have variety of terms I minus 1 j plus 1. So, this term, then we have I j plus 1 2 times. So, I j plus 1 2 times. Okay. So, this is, see we have 2 get cancelled. So, we have to do some exercise here. So, 2 get cancelled, okay. Then 2 get cancelled, right. So, we have u I j plus 1. So, let us collect the coefficients u I j plus 1. We have lambda square here then plus 1, then u I j minus 1. So, we have minus lambda square because there is a minus sign. So, similarly here minus lambda square and plus 1. Okay. So, these terms are done. Then so u I minus 1. Okay. So, u I j plus 1, u I j minus 1 here. Okay. So, this is, so I will come back to you with on the lambda. Then similarly, we have other terms. So, these 4 terms are taken care. So, u I minus 1 j minus 1. So, you can, this is the term. Okay. Then u I j minus 1. So, these are the terms. Okay. Then similarly, I plus 1 j plus 1, I plus 1 j minus 1. So, I plus 1 j plus 1, I plus 1 j minus 1. Okay. So, this is for a special case. So, this is a special value of lambda, but we can get a more general formula from here that involves lambda. Okay. So, this gives implicit method, and then you can see left hand side you have values corresponding to j plus 1, and right hand side you have values corresponding to jth level, and hence you get a system of equations. Okay. So, we will pay more attention to the implicit method in the coming lecture. Until then, bye.